turn my mic up as well. Okay, so now everybody should hear me again, and maybe I hope the others as well. And I have the pleasure to introduce our final speaker for today, which is Noa Marom. She is an associate professor at the Material Science and Engineering Department at the Carnegie Mellon University in the US, where she and her group combine quantum mechanical simulations with machine learning and optimization algorithms to computationally discover and design materials with desired properties for various applications. From 2013 to 2016, she was an assistant professor at Tulane University after a postdoc at the University of Austin. She is a member of the Pittsburgh Quantum Institute and affiliate of the Scott Institute for Energy Innovations. Professor Marom has received numerous awards after her PhD in chemistry, which she received at the Weizmann Institute of Science in Rehovot, Israel, for which she also received an award, which include the most recently the Dean's Early Career Fellowship from the CMU College of Engineering and the OpenEye Outstanding Junior Faculty Award for the Computers in Chemistry Division of the American Chemical Society. Her research interests, while not centered on tribology directly, are very broad, from materials for quantum computing and organic solar cells to molecular crystals. Today we will hear her talk about interface modeling, which connects very well to Clelia's talk earlier, and implying several models for machine learning and Bayesian optimization and so on. With that, I invite Noa to share her screen and have fun with the presentation. She reminded me just in the break that if you want to ask questions during the talk, please feel free to do so. I will relay them to her, and we can keep this a little bit more interactive. So Noa, please, you can start.
Okay, thanks for having me here. So the topic of my talk today is first principle simulations of hybrid interfaces. And what do I mean when I say hybrid interface? That means an interface between dissimilar materials, like a semiconductor and a magnetic material, or a semiconductor and a superconductor. And the nice thing about these interfaces is that when you put these materials together, you can get physical properties and functionalities that you can't get out of any of these materials separately. So having an interface between two materials allows you to achieve unique functionalities. For example, at the interface between a ferromagnet and a semiconductor, you can get, I'm sorry, my cats are fighting in the background. So at this interface, you can get spin injection from a ferromagnet into a semiconductor, and that can enable the implementation of spintronic devices. And then the superconductor semiconductor interfaces are of interest currently for the potential realization of quantum bits based on Majorana fermions. So that's the motivation for studying some of these interfaces. And of course, there are many other interfaces that are of interest for various purposes. And our goal is to develop general purpose computational tools for simulations of interfaces, which includes predicting the structure of interfaces and also their electronic and magnetic properties. And why are computer simulations useful? First, they can help interpret experiments. For example, if you have a spectroscopy experiment, it can help assign spectral features to specific structural features. And then another useful thing is, the space of materials that you can use to make interfaces is very large. And so we can many possible interfaces. So with simulations, we can help experimentalists determine which interfaces might be worth pursuing. So with that said, I'm going to start by telling you about how we predict the structure of epitaxial inorganic interfaces. So, sometimes, or in many cases, epitaxy is between two materials that are lattice matched, and their lattice parameters are very close. And then the film will just grow continuously on the substrate. But you can also have domain matched epitaxy between two materials whose lattice parameters are mismatched if you have supercells with integer numbers of cells of each material that form a commensurate interface. And there's an algorithm called the Zurn-McGill algorithm that can help you find commensurate supercells within a given mismatch and area tolerance. And we implemented this algorithm. So here you can see the results of a Miller index scan of the interface between aluminum and indium arsenide. And what that does is it goes through all the combinations of Miller indices of substrate and film, and it'll find all the possible domain matched interfaces within your misfit tolerance and area tolerance. So as you can see here, you get a very large number of candidate interfaces with these tolerances, 116 domain match structures. And this graph here shows you the lowest area misfit for each combination of substrate and film Miller indices. And you can see here that 3 combinations are the best. We have 111, 111, and then aluminum 011 on indium arsenide 111, and 012 for both combinations. So 012 is not, it's a somewhat higher Miller index, so it's not something that's typically used. So we're going to go with the 111 substrate. And then of these two interfaces, the 111 on top of 111 has a slightly lower misfit. So it's somewhat more likely, and we're going to focus on this one. So what we do next is what we call surface matching. So even if you have a domain matched, lattice matched interface, there's still the question of the interfacial distance in the z direction between the substrate and film, and also the in-plane registry between the substrate and film that need to be optimized. And it's better if you can do that with some low-cost computational method. So to this end, we developed a geometric score function that is based on the overlap and empty space between atomic spheres at the interface. So it's purely geometric. And the overlap term is here, it's squared, and then it's kind of an effective repulsion term. And the empty space here has the C parameter in front of it. And the C parameter is a system-specific parameter that we can also determine without any input from first principle simulations. So our experience has shown empirically that when the okay, let me start the story from here. So here you can see the z distance curves, and the dashed line here is the density functional theory reference. And then all of these different curves in different colors are the score function curves that you get with different C parameters. So you can see that the C parameter significantly affects the shape of the curve. And we define delta S 0, that's when C is equal to 0, is this distance here, and then delta S of C is this distance here. And we find empirically that when the ratio of these two distances is equal to 0.1, you get the best agreement with DFT and the position of the minimum. This is an example for tin telluride, calcium telluride interface that you can see here. So with that C parameter, you can see here that the score function is in very good agreement with the density functional theory reference, and it gets the positions of the extrema, the minima, and the maxima correctly, which is pretty good considering that there's no quantum mechanical information going into this score function. So after we do lattice matching and then we do surface matching for all the lattice matched candidates, we have to rank the resulting interfaces in order of stability. So in principle, you could do that with DFT. And we have the definition here of the interface energy, which is the energy that it takes to eliminate two surfaces and create the interface. So we have the two surface energy contributions here, and then you have the adhesion energy between the substrate and film at the interface. And the adhesion energy is defined as the energy of the isolated substrate plus the energy of the isolated film minus the energy of the interface, where all of these are DFT total energies, and they're divided by the interface area. So this interface energy has to be converged with respect to the number of film and substrate layers. And the reason is that you need the number of layers to kind of approach the bulk limit in order to get the asymptotic value of the interface energy. So here you can see for the aluminum indium arsenide 111 interface, the red curve is when we change the number of substrate layers and keep the film layers fixed. And the blue curve is when we change the number of film layers and keep the substrate layers fixed. And this dashed line is the average, and you can see that ultimately they go to the same converged value. So this you can calculate, but it's a pretty computationally intense calculation because of the fact that you have to converge the number of layers, and you end up doing pretty large calculations. So is there a quicker way of getting a rough estimate for relative stability as well? For this, we have a ranking geometric score function that's based on the overlap between atomic spheres, where we compare the overlap of spheres at the interface with an overlap of spheres in a purely film slab. That's illustrated here. We take these three layers and we look at what happens at the interface compared to what happens in the pure substrate. And then we do the same for the film, what happens at the interface compared to the pure film material. And the idea is that the smaller these differences are, the more similar the interface environment is to the bulk environment of this material. And so that would make for a more stable interface. So again, a pretty simple, kind of simple-minded geometric idea, but you can see that we get a ranking that's in agreement with the DFT ranking, which is pretty good for a crude geometric model. So when we get to this point, we see that the interface that's ranked as the most stable using the score function and DFT is in agreement with the interface that's observed experimentally in high resolution TEM. And so that shows you that we can predict the structure of ideal domain matched epitaxial interfaces by lattice and surface matching. So are there any questions on this part of the talk before I move on?
Maybe I can ask a question. Or there's someone else as well?
Sure. No, that was me. Just saying that there's nothing in the chat so far. But please, go on. Yeah. Ask a
Just
question.
a curiosity. Have you noticed any sensitivity of DFT to the ranking, depending on functional spaces?
So we haven't tested different functionals for the ranking. And actually, that's a good lead question for the next thing I'm going to talk about.
Cool.
So because of the computational cost of these simulations, we can only calculate these interfaces with semi-local DFT or DFT plus U, and what we use is DFT plus U, which brings me to the next topic.
Maybe I can interject and ask also a small question.
Thanks.
On one of the previous slides, you had an interface composed of one, I think, aluminium, and the other one was, I guess, also this indium arsenide. So how, I didn't know if you mentioned it, but I didn't get it at least. If you have a surface of one of the crystals or one of the slabs, let's say that has two different possible terminations, would that be?
Yeah.
So how do you deal with that?
So in this case, we knew what termination they had in the experiment. They had arsenic terminated substrate, so we used arsenic termination. But if you don't know the termination, then you can do both of them.
That makes perfect sense, of course. Thank you. So that will be also possible in the code. It will just check both. Or,
yeah, and you'll have to check both, and your C parameter will be different for each one.
Yeah.
Okay, so now that we have the structure of the interface, we want to study its electronic properties by the DFT plus U method, which I'm going to describe momentarily. And we machine learn the value of U for each material. So I'll start by explaining a little bit about density functional theory. That's the method we use to calculate electronic properties of materials and interfaces. And the idea of density functional theory is that you can use the electron density as the basic variable instead of the many-body wave function. And intuitively, it makes sense because the density is actually an observable that you can measure in an experiment, whereas the many-body wave function is not an observable. So what guarantees that we can do that, use the density instead of the many-body wave function, is a theorem called the Hohenberg-Kohn theorem, which proves the one-to-one correspondence between the electron density, the external potential, and the many-body wave function. And the reason why this is so good is that the many-body wave function is a bit of a monstrosity. It's a function of 3n spatial coordinates, where n is the number of electrons, which can be very, very large, even in a small system. Whereas the electron density is a function of 3 spatial coordinates. So you can go from 3n variables to 3 variables with no loss of information. And now we need a way of finding the ground state density. And for this, we have an equation called the Kohn-Sham equation. That's the basic equation of DFT. And it describes a mapping of the many-body problem onto an effective single particle problem, which results in this eigenvalue equation with this effective Hamiltonian, where you have the kinetic energy, the potential of the nuclei, the electrostatic interaction between electrons, and then there's this exchange correlation potential where all the many-body effects are buried. And you can see here that the Hamiltonian actually depends on the density. So you have to solve this equation self-consistently. You diagonalize, get a set of eigenvalues and eigenfunctions, construct the density, plug it back in, and so on until you reach convergence. So the only problem is this exchange correlation functional is not known exactly, and so it has to be approximated. And this is why DFT is exact in principle, but approximate in practice. So that brings me to the next point, which is in order to solve the Concham equation, you have to discretize it in a basis. And a lot of DFT codes use a plane wave basis set, which is a very convenient choice for periodic solids. However, an interface doesn't have a 3D periodicity. And so in order to deal with that, we have to, first of all, make sure that our interface model is commensurate in the XY plane, which may require a large supercell in the XY plane. And then we have to make sure that we have enough layers of each material to avoid quantum confinement effects and reach the bulk limit, which makes the simulation even larger. And then if we want to simulate a surface, then we have to add vacuum space to our model in order to avoid interactions between periodic replicas in the z direction, which makes it larger still. And then finally, if we want to eliminate spurious states from dangling bonds, we also need to passivate the surface with pseudohydrogens. So that means that simulations of interfaces can be technically involved and computationally expensive just because the interface model ends up being very large. So within DFT, we have different approximations for the exchange correlation functional. And one of the most popular approximations is the PBE generalized gradient approximation. And the reason it's popular is that it's very computationally efficient because of its locality. However, the problem with it is that it suffers from a problem called the self-interaction error, which is a spurious repulsion of an electron from itself. And as a result of that, the band gaps of materials tend to be underestimated, sometimes to the point that a narrow gap semiconductor like indium arsenide will turn into a metal. And this is what you can see here. There's no gap here. And so that's pretty bad news for indium arsenide. So there are more accurate approximations called hybrid functionals. And the reason they're called hybrid is that some fraction of exact exchange is mixed with the semi-local exchange and correlation. The problem with the exact exchange is that it's a non-local operator, and so it's an order of magnitude more expensive to calculate. So you can see here for indium arsenide, the HC hybrid functional does produce a band gap, and that's good. However, its computational cost is so high that we can't use it for these large interface model that we actually want to calculate. So that's a problem. And the compromise is what we call DFT plus U, where a Hubbard U term is added to the DFT energy. for certain orbitals to correct the self-interaction error. And we have an effective U parameter that is the difference between the on-site Coulomb repulsion U and the exchange interaction J. And so that's being added to the DFT total energy. And the advantage of this is that it has the same computational cost as semi-local DFT. The problem with it is that now you have this effective U parameter, and it's a system-dependent parameter, and you have to figure out what value of U to use. And in order to determine the value of U that we want to use, we developed this method of machine learning U by Bayesian optimization. So Bayesian optimization is an algorithm for finding the extremum of what we call a black box function. So you don't know the form of the function, and you want to find its optimum with a minimal number of function queries. So you know what the function value is in a few points, and then you build a surrogate model to guess the form of the function based on the points that you do know. So we, in order to perform Bayesian optimization, we have to define the objective function that's being optimized. And we define an objective function that is meant to reproduce the HSE band structure and band gap as closely as possible with PBE plus U. So it has two terms. One term is just the difference between the band gaps, and the other term is what we call delta band, and this is the qualitative features of the band structures. So we take the difference between the energy, the band energy of HSE and PBE plus U at every point in the band structure, and we shift both the top of the valence band and the bottom of the conduction band to 0 in order to eliminate the effect of the gap and just consider the qualitative features of the band structure. And we sum over a chosen number of bands, and then we sum over all the K points in each band and divide by normalize by the total number of energies we sample. So that's delta band. And alpha 1 and alpha 2 can give different weights to these two terms. So let's see how this works for indium arsenide. So the Bayesian optimization has the Gaussian process predicted mean, which is our guess of what the objective function looks like. And then we have an acquisition function, which determines where to sample the next points. So you can see that in the beginning, you kind of sample randomly, and we have like no idea what the objective function looks like. But after several iterations, it converges to this region. In the optimization, and this is a 2D optimization to find the U parameters for the p orbitals of indium and arsenic. And in the end, this is the PBE plus U BO band structure, and this is the HC band structure. And you can see that we have a similar band structure and we have a band gap, which is good. So now we can go ahead and simulate interfaces with indium arsenide. Okay, so any questions on this before I move on to some applications?
I see a question in the chat.
I think that was actually related more to the last part, so maybe we should put it in the end. I have a question to this part actually.
Yeah.
So how I mean, how do you select the orbitals if you I mean, of course, the intuition that you know, like as a chemist, of course you know which orbitals to select. But if you have you automated this in some way that that for example, if you have a material that contains 3 different species, you will like optimize like d orbitals for this and p orbitals for that, and yeah.
Yeah, so we can project the band structure on the different orbitals to see the contributions of different orbitals. So so you can see here, for example, that the arsenic p orbitals and the indium p orbitals contribute here to the top of the valence band and the bottom of the conduction band. And so these would be the orbitals that you want to apply the value of U to. So by resolving the band structure to the contributions of different orbitals, you can figure out which orbitals to pick for Bayesian optimization.
Okay, so basically you would have to do some, I mean, some initial HSE and PVA calculations anyway, and you just project to the region.
We have to do we have to do an HSE calculation as a reference for the Bayesian optimization, but we do that calculation only once for the bulk material, for the primitive cell, and then we go on and do the big interface calculation with the PV plus U. And
how, I mean, I imagine you must have tested this and done this quite a lot of times. So are there any materials where you get like some really unexpected U values compared to what usually is used in literature of like a couple of like 2 to 5 eV 4D materials or something?
So the negative U values for
I was pointing to that, yeah.
the p orbitals are somewhat perhaps somewhat unexpected. Although there have been reports of negative U values in the literature previously, but it's not widely used. The reason they're allowed is that the effective U is actually a difference between U and J. So if J is larger than U, it can be argued that a negative value is permissible. And then maybe you can rationalize it with the fact that how the self-interaction error works for d orbitals versus p orbitals, that d orbitals tend to be overly delocalized and maybe the p orbitals tend to be overly localized. It's not well studied on, let's say, on formal grounds, but empirically it has been found to work by us and others.
Okay, thank you. Makes a lot of sense, yeah.
Yeah. Okay.
So I think we can go on with the applications.
Okay, so in the remaining time, I have a few applications to show you for topological interfaces. So let's start with a crystalline topological insulator. The rock salt structure of tin selenide is an example of such a material. So topological crystalline insulators are materials that in the bulk are just insulators with a band gap, but on the surface, so here you can see a slab model of tin selenide with surfaces. And here you can see the band structures of this model. And you can see that on the surface, you get this conducting state with a Dirac point, and that's the topological surface state. And the reason you get it on the surface is that it breaks the symmetry of the bulk. So now we want to know if we can somehow open a band gap in this topological state in order to be able to use it for devices. So at an interface with a ferromagnet, the time reversal symmetry is broken, and then you can open a gap in this topological state. And you can see in this case, we open a little gap of 21 millieVs at the gamma point and 9 millieVs at the end point, with when it's interfaced with europium sulfide, which is a ferromagnetic insulator. And it may seem very small, but it's actually larger than the previously proposed materials combination. Another interesting thing about this interface is that when you, so this one was a periodic heterostructure model where you have interfaces on both ends. But when you have a model of the tin cyanide being grown on top of the europium sulfide, and then you have a top surface here, then you actually see that it's split into two Dirac cones. And the green one here is the one that's on the top surface. And you can see that it's not shifted and there's no gap in it. Whereas the one that's here in contact with the europium sulfide at the interface is shifted from the Fermi level and has a gap. So that tells you that this effect of the interface is very localized. You only get it at the interface, and then the top surface is not affected. So that's one story about topological insulators and how you can manipulate their properties by interfacing them with other materials. And then another story is what we call a 2D topological insulator. So that's a topological insulator phase that can emerge at an interface between two materials that are not topological insulators themselves. So here we have two materials. Cadmium telluride is just the wide gap semiconductor. And then mercury telluride is a semi-metal, and it has an inverted band structure, as you can see here, where the mercury S states form the top of this band here, and the P states form the bottom of this band, the tellurium P states. Okay, so what happens if you interface these two materials? Something very interesting. So if you have a small number of layers, you have just a trivial insulator at the interface. And here you can see the top of the valence band is made of the tellurium P states, and the bottom of the conduction band is made of the mercury S states. And as you start adding more and more layers, eventually you get this band crossing. And as you add more layers, you get this inverted gap opening with the band character changing. So here the bottom of the conduction band changes to tellurium P, and then the top of the valence band changes into mercury S. So at a critical thickness of 5.1 nanometers, you have this magic happening where two materials that are not inherently topological insulators silently produce a topological insulator phase, inverted band gap. And if you keep adding more and more layers of mercury telluride, eventually you'll get this bulk band structure. Okay, so the next question is whether a 2D topological insulator phase can be produced between two materials that don't even have an inverted band structure like the mercury telluride. So two completely regular, boring semiconductors gallium antimonide and indium arsenide. So it has been proposed that under the right conditions, so at this interface, you can see that the top of the valence band is made of gallium antimonide states, and the bottom of the conduction band is made of indium arsenide states, because that's how the bands line up. So it has been proposed that under the right conditions, you could raise the gallium antimonide top of the valence band and lower the indium arsenide bottom of the conduction band, and get these bands to cross, and then get an inverted gap to open. And you would theoretically achieve this topological insulator phase. There's some debate over whether it's actually achieved in practice. And so we wanted to see by computer simulations maybe what would be the right conditions. So we started by looking at trying to find a critical thickness where this band crossing and inversion might be achieved. And you see here, this interface, first of all, has two types of terminations, where the indium can be in contact with the antimony, or the gallium can be in contact with the arsenic. And it makes a difference which interface type you have. And so here you can see what happens if we add layers of either material. And when we add layers of indium arsenide, as you can see here, on top of 50 layers of gallium antimonide, the band gap does narrow, but it doesn't close. With up to 50 layers, which is 50 nanometers, we don't see a band crossing here. And it seems like maybe the asymptotic limit is going to be some finite gap here. The indium antimonide type interface has a narrow gap. So we can't get the bands to cross here just by adding layers of indium arsenide. The next thing we tried was adding an external electric field. So because of the computational cost of the simulations with the electric field, we can only do it for a model with 10 layers of each material. So that means that it has effectively a larger gap because of quantum confinement. So we're going to need a larger effective electric field to close the gap here. But you can see that if we apply a large enough electric field, we do get the bands to cross, and eventually we get an inverted gap to open. The inverted gap will widen but also shift higher above the Fermi level as you increase the electric field, which means that, first of all, you'll need a considerable electric field in order to produce this band crossing. And second, you would need to somehow tune into this gap, which is above the Fermi level, in order to observe it. So we tried to estimate what would be the effective field that might be needed for a larger interface model, just by looking at the change in the band gap versus the electric field. So here you can see the slab with the 10 layers of each material, the indium antimonide type interface, where you need a lower electric field here to close the gap than for the gallium arsenide type interface. And if you had the 50-50 interface with 50 layers of each material, then we estimate that you would need a smaller electric field to close the gap because it's narrower. It's a narrower gap to begin with. So this is how you would maybe be able to produce the topological state between two conventional semiconductors, but it seems like the conditions to achieve this are not trivial. So this brings me to the end of the story. So just to recap, I told you about how we predict the structure of epitaxial interfaces, and then what we do to predict their electronic properties with DFT plus U.
So, thank you, Noa,
Thank you,
for
Noa.
this great talk. So I actually raised my hand. I wanted to applaud. We don't have really much audience reaction, unfortunately, in the Zoom call because we have the audience on YouTube. But I think this, especially probably for computational tribologists, this Bayesian optimization of the U is tremendously interesting. I mean, not to mention the efficient sampling of interface structures. I mean, for now, in most of our simulations, DFT is still the gold standard, just standard PVE usually. But with basically no added cost to get more accurate band structures. It is quite exciting, I think. We actually do have a question in the chat now. That is, I think, referring. Yeah. Okay.
Just one more thing about the interface configurations. I think that for getting the right interface distance and registry, especially for the interface distance, the van der Waals correction is probably more important than the DFT plus U. We do use the van der Waals correction in our interface simulations, but then the U is critical for the electronic properties.
So I was actually going to ask about the van der Waals corrections, and I was wondering whether the kind of do you use the standard post DFT Grimme correction, or you have other?
We use the Tkachenko-Scheffler correction.
Okay.
It's a pairwise correction similar to the Grimme correction, but the difference is in how the parameters of the correction are derived.
Okay, cool. Thank you.
We have I didn't show it today, but we have a paper on the indium arsenide europium sulfide interface, and then that goes into the details of that a little bit.
Is the van der Waals, do you think the van der Waals effects are also somehow affected by the number of layers that you manage to include in your the extent of the van der Waals correction?
We didn't really test that. We just kind of use a sufficient number of layers to converge it. We do find that it takes more layers to converge the electronic structure than to converge the structure. In order to reach the bulk limit where you don't have quantum confinement, it can take a very large number of layers, depending on the material. But we find, for semiconductors like indium arsenide and indium antimonide, something like 40-something layers. For materials where, for semi-metals and topological insulators where you have to close a gap at the interface, it takes a very large number of layers. For alpha tin, for example, we find that it takes 80 layers to really close the gap. And then for the topological insulators I showed you for this work, it also took a very large number of layers. I don't remember off the top of my head how many, but it's in the paper. We needed a very large number of layers to really close the gap at the Dirac cone.
Interesting. Thanks.
I think the question that is in the chat is somewhat related to this. I mean, this is going back to, I think, geometric optimization. So in the first part of your talk, when you talked about converging or actually, yeah, total energy, I would say it was probably the interface energy, so that you converge the interface energy with respect to both the top and bottom slab thickness. And the question is from Fiat Yalchin, and he asks, I was wondering if you have an intuition as to whether or not optimizing film and slab thicknesses separately, for example with respect to the surface energies, would give similar adhesion energies as your method.
So we find that optimizing them separately can lead to a different number of layers than if you optimize them together, which is why we do that. But the surface energy does also go into the interface energy, so we also have to optimize them for the surface energy separately.
So basically you have to do optimization for each of the slabs with respect to surface energy, and then with them together in all the combinations to get a total interface energy that you got that you're sure is correct.
Which again makes it a pretty expensive and time-consuming calculation. It's a lot of effort to calculate an interface energy, and that's why we have a kind of quick and dirty way of trying to estimate it without doing DFT calculations.
Yes.
And then you can do DFT calculations for your last maybe 1 or 2 or maybe 3 candidates if you really want to figure out which one is the right one.
Yeah, I mean, if you do a complex enough systems, even the calculation of a surface energy becomes complicated. Maybe, yeah, or at least cumbersome.
Right.
I'd say not complicated by the method, but
No
expensive.
doubt.
Yeah. Okay.
Yeah, we have another paper on surface energies of organic molecular crystals, where because the organic molecules are very large, when you start adding layers of a molecular crystal, it becomes really large really fast. So surface energy calculations also can become very expensive.
One small thing that when you talked about this in the last section about this this need for very large layer count. So in my experience, if I make my cell really large, I get really problematic convergence behavior, at least with WASP. I'm not sure what codes you use,
Right.
but this high asymmetry of the cell is not playing really well with the code, it seems. So do you see something like this, or is there a way to correct?
Absolutely. We do see convergence issues with some of these large interface calculations with VASP. We do use VASP. My students work very hard to try to figure out how to converge these calculations. And we did put in our papers the parameters, the flags we used in VASP in order to get them to converge. And it's especially tricky when you have magnetic materials. The calculations just can get very painful to converge, and like half the time the SEF doesn't converge. And we have a paper that we just put on archive last week on an interface between Heusler's and 3.5 semiconductors, and we in there we put the VASP flags that we used in order to get them to converge.
I will be sure to look that up just for that. I mean, also I'm interested in this work, but yeah, just because I mean I don't know if you know, but I'm also working part-time for the WASP company, so I'm also interested in like special complicated cases and test sets and so on. Okay.
Okay, well, if you also work for the WASP company, then I should mention that we have visualization package for VASP called VastVis, and it's described in this paper, in addition to a few other things. This paper is a review paper called Best Practices for First Principle Simulations of Inorganic Epitaxial Interfaces. And there's a lot of good advice for people who want to do simulations of interfaces. And also we use this VastVis visualizer to make all kinds of nice plots with projections of the band structure on different atoms and different orbitals and different spin states. We can do interface layer by layer local density of state plots. They're also very nice for interfaces to see. They enable you to see things like band bending at the interface and metal-induced gap states and proximity-induced magnetism in the semiconductor, all these things. Also, it works with VASP and also can be useful for VASP users.
Okay, I think I've already seen the paper. I'm pretty sure I consulted it before for some specific questions I had. I'm not remembering now what these were, but I'm familiar with the title and I'm sure I've seen it. I would be interested. I will check out this VASP visualization tool. I mean, you might know that VASP is slowly switching to a different outputs format, HDF5, and with that comes also different analysis tools. But this is early stages, and of course inspiration is always welcome. And third-party
I guess we'll have to update our package then.
I mean, no, not now, not so quick. There will be the old output files will continue to exist for some while, but I think we all can agree that the XML file is not ideally to parse. And yeah, so hopefully this will be easier in the end. Yeah, there will be a nice Python interface and so on. Okay, with that, if there are no more questions, either from the panel or from the chat. In the chat, at least, I don't see anything. If you are in the panel, please raise your hand or just unmute yourself. But if there is no more, I think we're pretty perfectly in time to thank all of the speakers again with our very small virtual applause feature here. And especially thank Noa for the last talk. And with that, I say goodbye. Have a good day. And I hope to see you next Friday for the next and last session of WeSST 2022.